Hello and welcome to another tutorial. We're going to continue our discussion with how to handle Java resources. In our example, it was reading data from some text file and how to deal with them or embed those resources directly in the native image, in the final binary executable file that the native image compiler creates, right? And we saw that we can read the text, a text file or any data, any stream of bytes. We can read them and bring them into our Java application using the scanner class. So whenever you want to deal with text, read text, understand them, or go through them word by word, line by line, your first thought should go to the scanner class. It's very powerful. It has a very versatile set of constructors, and you can even define how the scanner can interpret those stream of bytes using the character set or char set. And I showed you there are many different ways, the char sets that Java supports. Basically UTF-8 is usually is the default platform encoding. UTF-16 is usually what Java supports, right? And we saw that if you want to read the text file, you have to pass it as a file object, because file object is an abstraction. You cannot pass directly the path to that file as a string, because the constructor of the scanner that takes a string actually tokenizes the string itself instead of assuming that it's a path to a file, right? So we can use the scanner class to read the text file. The path, relative or absolute, should be passed to a scanner as a file. And again, this file object handles basically the underlying operating system's file system, and it can work with both absolute and relative path. So both of them are supported. And whenever you pass a relative or absolute, you can also, the file object has methods for retrieving, for example, where this basically file is, an absolute path or relative path. There are other things like canonical path, etc., right? And we will look at the methods inside the file object. We want to have a platform independent representation of the resources, and this was one of the examples that we discussed in the previous lecture. So if you use a file object and give it a relative or absolute path to where the resource is and then pass it to a scanner, obviously that resource is directly tied to the underlying directories at the operating system. So if I give my Java application to somebody else, they might have that resource file also. I can package or bundle that resource file, let's say a text file, into my jar file. But then the problem is that they might not have the same file structure, the directories. So really it's not a good idea to have a file that is or basically a resource that our Java application uses that is directly tied to the underlying file structure of the operating system. We know that Java is all about platform independence. So how do we do this? JVM has a platform independent behavior. That's the whole meaning, right? If I write a Java application, if I bundle all the resources with it, I want to give it to somebody else, and because they already have their JVM, even if their operating system is different, even if their CPU is different, as long as there is a JVM is available for their platform, I want them to just get my class files or whatever application is. Let's say I package it as a jar file, give it to them, and I just want them to run it successfully, right? So portable code, that's the whole meaning, right? Write once, run anywhere. And unfortunately, again, the loading resources, if you just use the file class, it's going to be tied to the operating system, the directory, etc. Accessing text files should be also platform independent. Is there a way to load a resource at runtime in a platform independent way? And the answer is yes. So if we hard code the path to a file in the source file in our Java application, then we can't really have a portable application, right? The code is not platform independent and probably not portable. Why? Because again, we're using relative or absolute path. First of all, it depends which directory is your working directory, where you run your Java application from, especially if you use the relative path. It also depends which working directory the Java application is run from, right? So especially when using relative path in the source code. So if you define a file and then give it a relative path, That means whatever the way Java interprets that is whenever it sees a relative path, it assumes that it's with the working directory, right? And the working directory for JVM is where you launch your JVM, which directory you launch your JVM. We said that inside terminal. The idea here is that inside a terminal, you are always in a working directory, right? CD desktop. And then I can write Java, and then let's say my application is in a format of a jar file, and give it a jar. And whenever I type Java, it means I'm launching a JVM. And the JVM understands that this current directory that I'm launching the JVM from is my working directory. So if in my source file source code I have something like dot something, right, and then some text file, some file .txt, then the JVM interprets this dot means the current working directory. In this example is desktop. So this is really limiting, right? This is not a portable code, because somebody else might want their Java application from some other directory. They might not have this directory on their operating system, so it won't work, right? So it's not really a portable code. So what is the solution for platform independent resource access? Let's say I want to access a text file and load it in a way that it really is not dependent on the operating system. You probably can guess that in that case, we're not really going to use a file class, because again, file class represents the underlying directory hierarchy, whatever is on the computer that we're actually writing the source code. There is no unique solution, but there is a good solution, or at least my recommendation. So it's best to rely on JVM, and JVM provides a way at runtime to load classes. So JVM has a mechanism, right? Because we know that JVM is a lazy loading machinery, which means whenever you use a type in your source code, like let's say you have a type called car, as long as you never use it, JVM won't search for a class file called car and never load it. But the first time you use a type, JVM searches for basically a file called whatever the type is .class, and then loads it into memory. How does JVM do that? It uses a concept called class loader. So class loader is a class that comes with the JDK. And I've said it many times that JVM searches for class files in a particular directories, which are called which are known at runtime in the class path, right? So class path is more or less abstracts a way where the JVM has to look into when it tries to find the resources. So class loader also works with class path, right? So class loader is the tool in the JDK that can locate the class file at runtime. What we do basically, we say class loader, there is a static method called getSystemResource. And a getSystemResource means whenever you deal with system, it means search for a resource that the system or the JVM understands, which means look into the directories that are on the class path. So class loader is like an abstract way of how to search and locate resources at runtime. Because at runtime, you have to always specify some sort of class path. Even if you bundle your Java application as a jar file, there is a manifest file inside of it that specifies how this jar should be interpreted, right? What's the directory hierarchy? What's the top level directory that will be added to the class path? So, and then this returns a particular object. Here I'm using var for simplicity, but in Eclipse, we will look at what exactly is the type of this resource that getSystemResource, which is a static method, returns. And then it has a method called getPath that gives you actually the exact path, the full absolute path of that resource, right? So what we're doing here, obviously, we are translating the file that we use to a resource that is available on the class path at runtime. And then the class loader can figure it out, and then after that we can get the absolute path, right? And again, this concept of getSystemResource from class loader is a platform independent code. It works on any platform, right? So on any platform, when the class loader searches for that resource, and this get path could be different depending on where that resource is. All right, let's head to Eclipse and try to have a hands-on experience with this. We had this code called class called resource demo, and we saw that we have a text file called runme.sh, It just has some simple characters in it, and we try to read it. We said that we have to give the scanner a file, and here I'm using the relative path. And the first question was, what is this relative path? And it depends on runtime, right? Wherever you launch your JVM from. And we know that in Eclipse IDE, whenever you run your Java application, the way Eclipse handles this, it creates a run configuration, and it sets the working directory to the top, the project folder, workspace project folder, right? That's how Eclipse IDE handles it. So some other IDE might handle it differently. That's why if I give you this code or even the class file and you run it in different IDEs, it might not work, right? Right now, this relative path is really tying us to the way the Eclipse IDE handles it. And we saw that so basically this dot at the moment inside the Eclipse IDE means this project directory, right? The top level. And my text file runme.sh is just inside this directory, right? And then this works. And then we said that, okay, this is not good. And even when we compile this to native executable file, we saw that this relative path is really interpreted the same way, which means the native executable file also interprets this dot as the current working directory, wherever we're running our native executable file from. And this doesn't work, but if I go up one level in the project root, and now I go inside the native directory and run it, it can find it because this dot is still interpreted as this working directory. And our native executable file searches from this current directory, tries to search for a file called runme.sh, and it can find it, right? So again, this is not the best idea. And the other thing is that if this file, ideally what I want is that this native, I want to kind of embed the contents of this text file inside my native executable file, so that I don't need to have to rely on this external file, right? That's something that's what we're trying to move towards it, right? So the first step, we want to get rid of this platform dependent file. And what we're going to do here is we're going to change our code a little bit. So instead of doing this, what I'm going to do, first of all, let's comment all this out. How else are we going to get access to this file, get access to this resource? So I mentioned we want to rely on the class loader, right? So so class loader, it's in the Java lang, it's automatically imported. And then if you look at the static methods, get platform class loader, this returns a class loader, get system class loader, class loader. And the difference here is that system class loader loads all the class files, third-party class files on the class path. Platform class loader loads only the JDK classes, the classes that come with the JVM. And if you are familiar with these a little bit in more details, you know that there are security levels that these class loaders have, or basically security clearances on what classes they can access and load. So system class loader means anything that is not part of the JDK, right? All the resources, classes that are third party. Get system resource. Again, these are the resources. These are files that are not class files, that are third party files. They're not part of JDK. Get system resource as a stream, and get system resource, you give it the name. Here you get system resources. So here you give it basically, if there are multiple files that have the same name, this can return all of them, right? So let's what we're going to do, we're going to say get system resource. And what is the name of our resource? Runme.sh. Remember, now we are not providing any path, any relative or absolute path. You just provide the name. And how does the class loader works? This system class loader, again, it works with the concept of the class path. Remember, class path abstracts away all the directories, where the resources are, where the class files are, where the resources are, right? So this returns something called a URL. We can just use .var template to create a resource. Now normally I prefer to just use var here, but the type here is URL. In Java in JDK we have two types, URL and URI. Normally URL is more URI is more like network stuff, the protocols that we use. URL, universal resource locator. This is an independent way or platform independent way. So the class URL represents a uniform resource locator, a pointer to a resource on the World Wide Web. These are also the concepts that came from networking. A resource can be something as simple as a file or a directory, or it can be a reference to a more complicated object, such as a query to a database or to a search engine. More information, you can find it here, right? So there is also URL, there's also URI. So Java Net URI represents a uniform resource identifier. Aside from some minor deviations noted below, an instance of this class represents a URI reference as defined by these standards, right? And again, these are more like network protocols, how the binaries get translated. But here the system resource returns a URL, which is again a more like platform independent way, because every platform, every operating system follows the same protocols when it comes to World Wide Web or networking, right? Networking are standards that are independent of the operating system platforms. I believe that's why Java adopted this. So what can we do with this URL? So let's look at the methods. It has equals, get authority, get class, get contents. Let me zoom out to look at the help. Get content, it returns an object of type URL, gets the contents of this URL. Get default port, obviously we're not using basically networking, right? This system resource doesn't come from the network, it comes from the class path. Get file, get host, get path. So get file returns the string, get the file name of this URL. So let's start with that. sysout resource.get file. And this returns a string. So let's see what we get here. Cannot invoke get file because resource is null. Why is it that? So obviously what happens here is that when this class loader searches the class path for a file or a resource called runme.sh, if it doesn't work, it returns null. So you should always do a null check to see if the resource was found or not. So if resource is not equal to null, we're going to say that get the file, right? Else we're going to sysout that resource not found. All right, let's run this. And this tells us that resource not found, which means the class loader wasn't able to find this resource. Why? It's already there. That's because now we are moving to a concept towards a platform independent way of locating resources. But again, JVM still needs to know where to look at, and JVM only understands class path. And you know, the way that Eclipse IDE organizes the class path is that at the moment the source project, the directory of the project, is not on the class path. Only stuff that are in the src folder are on the class path. So what I can do first is to move this runme.sh inside the src directory, right? And now Eclipse, actually, if you look at the hierarchy, anything that is inside src, Eclipse copies them also to the bin directory. So if I look at my src directory, you see that the runme.sh is now, so actually if I look at my bin directory here, you see now runme.sh was copied. If I move it back, you see Eclipse removes it also from the bin directory. So I'm going to move this to src directory, which is a source directory. And now if I run this, it's going to work fine, because now this runme.sh at runtime, it's available on the class path, which means it's inside one of the directories that is on the class path, right? And now it works. And you see now if I give this application to somebody else who is using another operating system, another computer, this will still work. This code is fully platform independent, and it has a platform independent way of locating this resource. Why? Because when they go and run the Java application, they have to specify the class path. That's something that mandatory. Whenever you want to launch a JVM to run a Java application, you have to provide the class path. JVM needs to know where to load all the class files, all the resources from. But then after that, everything else is in this code is platform independent, because this class loader, based on where you run your Java application, just searches into the class path and then finds this resource. And interestingly enough, when you get the file or get the path, it tells you exactly, gives you a platform dependent representation of the file. So on Windows, you probably get C:/ something. On Mac OS, you start from the root, etc. Right? So it's very interesting that we are loading this resource in a platform independent way, but then the absolute path to the file can be a platform dependent thing, which is very nice, right? This is one of the nice capabilities of JVM, because you can load the resources in a platform independent way. Now there was another option in this for this resource, get path. Let's also try that. Get path returns a string, and they kind of work the same way. There's not difference in this, right? All right, so so these two at the moment for a file that is working at the resource, get path and get file are more or less the same thing, right? And so right now we have been able to successfully load this resource in a platform independent way. The key is to make it available on the class path at runtime, right? So the key here to make the resource file available on the class path at runtime. This is the key, right? Because after that, everything else becomes platform independent, which is very nice. Now, if we do this, how do we basically now read the contents? Let's say we get this URL. How do we do this? One thing that we can do now, obviously, instead of hard coding this string, we can ask our resource to get file, right? What this does is now it gets the absolute path and then pass it to the file, which is a abstraction of the underlying file system of the operating system. And hopefully this still works fine. Yes, this works fine. All right. However, let's see what happens now if we go ahead and compile our Java application to a native executable file. Again, class loader, this kind of stuff, they're fully supported with the native image compiler because they're part of the JDK. Anything that is part of the JDK is fully supported, so no worry about that. So we select our Java file, resource demo, and we run our native image, and we see what's going on. So it's preparing to compile. Just note that this get system resource, if it doesn't find it, so it has a unchecked exception, right? Null pointer exception. So we're getting a warning, and the warning is that, hey, resource access method Java class loader invoked at main method, right? So native image compiler realizes that you're accessing a resource in a platform independent way. And native image says that I don't know what this resource is. So what it did, it actually failed. We've seen this before when we look at the reflection. And now it's basically it goes to a fallback mode, which is creating an executable that needs to be backed up by a JDK. So if we look at this and open a terminal here, so if we say this one, it says that it's a fallback, so it cannot run, right? So native image failed because we're accessing a resource, and previously we said that anything that has with some sort of runtime stuff that cannot be figured out at compile time has to be fed as extra information to native image compiler. And how do we do this? We did this for the reflection part using the Java trace agent. So we have to run this with the Java trace, which is the JVM that comes with the native image, right? With the GraalVM. So let's run our Java application with the JVM that comes with the GraalVM, and it creates this meta-inf and then native image. And then if you now look at the resource, interestingly enough, now basically native image agent that came with the GraalVM JVM realizes that we are accessing a resource, runme.sh, right? And it means that this has to be available on the class path. And when we run our compilation with the native image, we select our source for resource and then native image. What it realizes that native image looks into this configuration file resource, and it tries to when it tries to compile, we said that you have to specify the class path for the native image compiler. So it is able to find this runme.sh on the class path at compile time, and now it's not going to complain about accessing a resource because it understands that this resource has to be available. And you see there is no warning. Native image was able to find this, right? Well, let's go ahead and run our this executable file. So if we say here, and still there is a problem here. So resource get file, resource get path, they are run this, but you see there is a difference. If I run my Java application, obviously I get this result and I am able to read the contents. But when I run with the my native image, I get a different result. It says /runme.sh. And the reason is that obviously when you compile to the executable file, there is no concept of like a kind of class path anymore. You just want to run your executable file. And whenever you run this, it still understands that file, at least the string or that resource, but it still says I cannot find that file, right? This file fails because get file returns this from the root of the operating system, go to runme.sh, right? Obviously this is not the correct path for this file. That's why our code at the moment is not exactly platform independent because of using this file. So we have to abandon the idea of using this concept of file. So if I want to use the scanner, I have to kind of feed this resource in another way to a scanner. And we already know what to do. So we saw that a scanner has another constructor that you can directly feed it input a stream, the stream of bytes. And interestingly enough, this URL, that resource that we get as a URL, has a method called so get authority, get file, host, get path, get protocol, get query, get ref, get user info, get class. So it has a open a stream. This open a stream returns an input a stream. And what this does, it feeds the scanner an input a stream that a scanner can read all the bytes, right, from that stream. And again, this becomes something that is platform independent. Now this is not tied. So using file ties us to OS. Using a stream or input a stream makes it independent. Makes it independent of OS, because we have a way of independently loading that resource. And now there is also a way to independently read all the bytes of that file, and a scanner understands how to translate those bytes to character. So if I run this as a Java application in my Eclipse, it still works. Nothing has changed. The only thing that has changed is that we're not using the file anymore, right? We're using the input stream that the resource provides. Still works fine, right? Now let's see what happens. Now we still need to run our Java trace. It will give us the same thing, right? So so I have to select my resource demo and then run the Java trace. It still tells native image in the configuration file. There is a resource config and we're using this runme.sh as before. So the native image compiler understands this file, can find it as at compile time. But now let's see what's happening. Now that we're using the stream, actually what the native image compiler does, it reads all the bytes of this stream and hard code them into the native executable file. So input stream, what happens is that the native image compiler at compile time, we give it the class file, the class path, and it accesses this resource and reads all the bytes, This obviously any compiler can read all the bytes of any file. That's fine, right? Any file is just a bunch of bytes. And then the compiler hard code them into the final executable binary, which is very interesting. So let's go ahead and select our, obviously we need to have this meta-inf and run the Java resource to tell the native image there is this resource we're accessing. But then now let's go and finally run our compiler native image to get the executable, and hopefully this time it's going to work. Our Java application, we're going to run it as an executable file. It's going to run. It's not going to actually depend on whether this runme.sh is available or not. It's completely independent of this file. All the contents of this file is already copied into the final binary file. And that's a very powerful concept using these streams and these class loaders. It's really something that makes this kind of native compilation very powerful. So if I open a terminal here and then say resource demo, now everything works fine, right? Java version, we were able to successfully read the contents because we're not relying on any file. Remember, this runme.sh is not available in this native directory folder. Doesn't matter. Even if I go up one level and then now say native, this works fine. The binary contents of this resource has been already copied into the final executable file. I want you to really understand this. In the next lecture, I'm going to show you an example where I have a very large file, text file. The size of this text file is going to be like 10 megabyte or so. And then when we compile our application and use read the contents, you see that this final size is like 25 megabyte because all the contents of this file have been already copied into the final file. So I hope you enjoyed this lecture. Please stay tuned and I'll see you in the next one.